Alright, let's get started with the first practice problem. The first practice problem is called 50-step assembly line. In this problem, the assembly line has 50 steps that are carried out sequentially. The key term here is sequentially. And each of these 50 steps has a defect probability of 1%. And the final product produced on the assembly line is defective if any one of the 50 steps made a defect. Then what is the probability of the defective product being produced? Well, we can think of this as the linear production model assembly line that we saw in the class. That is, the product is made by going through a serial 50 steps, and the product would be called good only if none of them make a mistake. That is, a product would be defective if just one step makes an error. So it's like asking the yield of the process. Yield of the process is what? Remember, when we know that the product is bad if just one step makes a mistake, then the yield of the process is nothing but the product of the yield of each step. So we know each step has an yield of 0.99 multiplied by 0.99 all the way 50 times, 0.99 50 times, or that is same as saying 0.99 to the power 50, which turns out to be 0.6050. That is the yield of the process. But the question asks what is the probability that the defective product is produced. So the failure rate P is 1 minus the yield of 0.6050, what is 0.3950. That is, there is a defective rate of 39.50%. The next question asks, at the end of the assembly line there are two operators independently inspecting the product. Each of them is going to recognize a defective product with a 90% probability. Assuming that the product is not defective, it's moved to the shipping department, otherwise the product is scrapped. What is the probability that the defective product is moved to the shipping department? Well, what needs to happen for a defective product to be moved to the shipping department? That means a defective product is not caught. A defective product is caught if just one person catches it, right? Here the yield for each guy is 99%, right? The yield for each guy is 99%, but this is not like the previous scenario where for it to be correct it has to be correct everywhere. Just one person has to catch it, then it's fine, right? So now the chances of them making a mistake or them not catching a defective product is 0.01, right? We multiply 0.01, the two failure rates, to get, the failure rate is 0.1. So we multiply 0.1 and 0.1, the two failure rates, to get the failure rate of the process, that is 0.01, right? And that's exactly what we wanted. The probability that the defective product is moved to the shipping department. Again, the interesting part here is, for it to be correct, right? For it to be correct, just one person had to do the job right. For it to be failure, both person had to make a mistake. Here, For it to be a failure, just one person had to make a mistake. That's why we multiplied the yield to get the yield. Here, to get the yield, we have to, if the question was the yield, there the question is the failure rate rather than the yield. If the question was to get the yield, we had to multiply the failure rates and get the failure rate. And if the question had asked the yield of the process, then we would do 1 minus 0.01, and it would be 99%. I like to remember this no matter how the question is asked, how the question is phrased. In this case, the defective rate. In this case, also the defective rate. No matter how the question is phrased, I like to think it in terms of yield. To get the yield in the serial process where one person makes a mistake, it is a mistake, you multiply the yields. Whereas in this Swiss cheese model, to get the yield, you just can't multiply the yields. You have to multiply the defective rates and then subtract it from the 1 to get the yield. If you remember that way, it's easier to keep things straight. So the answer for this is here. The next question. For the next question, the paper here is not enough, so I'm going to move to a blank page here. Alright, now we're ready to start with the second problem. Problem with scrap. Problem with scrap. In this problem, what's going on is there are 4 steps in the process. Again, this is a process analysis. So we make 4 steps. Call this resource 1, 2, 3, and 4. The processing times are given to us. The processing time for the first resource is 5, and there's only 1 worker. The second resource has a processing time of 4 minutes. The third resource has a processing time of 20 minutes, but there are 2 workers. The fourth one has a processing time of 12 minutes. These are all in minutes. Given the processing time, we can calculate the capacity. The capacity is 1/5, 1/4, 1/20th, 2/20th is the same as 1/10, and 1/12 units per minute. Well, if there was no scrapping, this problem would have been pretty straightforward, and we could find the bottleneck right away. But that's not the case. The second step here has a scrapping rate of 80%. That is, out of the 100 parts it works, 80 of them goes to scrap. Alright, then what's going on? As soon as there is a scrapping problem, the trick is to think of what happens when there was a demand of D. Suppose there was a demand of D. There was a demand of D. The fourth resource would have to work on D units. The third resource has to work on D units. The second unit, that's kind of tricky. Out of every 100 parts you produce, you throw away 80 parts. That is, to produce 1 unit, you throw 4 times as a scrap, so you really work on 5 D units. The real formula is, for the scrap, 1 divided by 1 minus the scrap rate of 0.8. That comes out to be 5. So if your D was 1D here, it would be 5D. But it is much more helpful to think of this more intuitively. If you are going to produce 1 unit, 80% scrap rate means you are throwing away 4 units, right? Out of the 100 units, 20 units go to the good, 80 units go to the bad. That means you are producing, for every 20 units, you're producing 80 units. That is, for every unit, you are producing 4 scraps. That means altogether you are producing 5 to produce 1 unit. So if he's producing 5D, he's producing 5D too. Well, after that, we have to calculate implied utilization. implied utilization, that is demand divided by capacity. So here the demand is D, capacity is 1/12, making this 12D. Here the demand is D divided by 1/10, that is 10D. 5D divided by 1/4, that is 20D. 5D divided by 1/5, this is 25D. So the resource with the highest implied utilization, that is our resource 1, is the bottleneck. So the first question, for every unit of demand D, how many units have to flow through the second step? Well, for D, altogether 5 units have to go through resource 2. That means for every 1 unit, 5 units have to go through step resource 2. That is the first problem. The second problem says, which process is the bottleneck? Well, as we saw, resource 1 is the bottleneck. The next question is about lean burgers. In this question, what's going on is the first question asks, what is the capability score? Capability score. The capability score, the formula for the capability score is USL minus LSL divided by 6 sigma. In this problem, the USL is given to us as the specifications are 95.5 grams minus 94.5 grams divided by 6, and the standard deviation is 0.25. So this is 1 divided by 1.5, so your capability score is 2/3. The second question says, what percent of the deliveries are likely to be outside the specification limits? Well, for this question, the specification limits, we assume this to be normal distribution. This has a mean of 95.5 with a standard deviation of 0.25. We are interested in these two lines, that is 94.5 and 95.5. Sorry, this was 95.0. Okay, so to find out what percent is outside of it, that is what is left of here, 95.5, right of 95.5 and left of 94.5, the trick always is to make another normal distribution, a very special normal distribution, which we call standard normal, that has a mean of 0 and a standard deviation of 1. And we plot this, we extrapolate this line and try to find what this equivalent lines are. Traditionally, these are called G values, so let's call this G1 and G2. So we are interested in G1 and 2. What is G1 and what is G2? The formula for Z, or any value corresponding to any other value in another normal distribution, is nothing but 94.5 minus this 95. So 94.5 minus 95 divided by the standard deviation 0.25. So this is 0.5 divided by 0.25 equals to -2. That was our G1. Our G2 is 95.5 minus 95 divided by 0.25 comes out to be 2. Right? If I look this at the normal distribution table at the back of the book, equivalent to this this minus 2, the left here is equal to 0.0228, and left of this 2 positive 2 is 0.9772, but we are only interested to the right of this, so it is 1 minus 0.9772, making it 0.0228. So the total outside these limits is 0.0228 plus 0.0228, which comes out to be 0.0456, that is 4.56%. Well, the next question is a lot easier. The question says, to what level should the supplier have to reduce the standard deviation of the operation if his goal were to obtain a capability score of 1? So his goal was to obtain a CP of 1. So again, the formula for CP is USL minus LSL divided by 6 sigma. We want the target CP of 1. USL is 95.5, LSL is 94.56, and we are interested in the value of sigma, or 6 sigma equals to 1, or sigma equals to 1/6. So if we have a sigma of 1/6, we'd get a capability index of